Sorry.
Hey Megan, are we ready?
And yeah, we're perfectly good. You're good to go. Thank you.
Okay, great. All right, welcome everybody for our seminar today. I do have one announcement that Matt Cohen, who's the director of the Water Institute, requested next Wednesday, and it will not be competing with the seminar, so you still have to show up to seminar. But Dr. Jordan Reed will be basically presenting the seminar for the Distinguished Scholars Seminar that the Water Institute has. The title of his seminar will be Advancing Water Research and Education, Kaushi's Vision for Community-Centered Infrastructure. And if you don't know what that Kaushi acronym is, it's the Consortium of Universities for the Advancement of Hydrologic Sciences. So if you have any interest or water connection, best thing to do would probably be to visit the Water Institute's website. Just Google it and then also look at their events that are coming up. It will be next Wednesday at 4 p.m. at Rights Union 2315, or it will be on Zoom, but we certainly encourage you to participate in person and ask questions. Definitely a worthwhile opportunity. So go to the Water Institute's website for that. So that's the announcement for today. Next, I'd like to introduce our speaker today. Dr. Rachel Rotz, who is a geologist and assistant professor at Florida Gulf Coast University. She investigates the dynamics between groundwater and surface water with a focus on terrestrial water quality and planetary hydrology. I had fun trying to look at some of the publications, and she's not virtually spent time on Mars, I guess, let's put it that way. Rachel explores water dynamics not only across Earth's diverse ecosystems, but also in extraterrestrial contexts. She actively mentors students, securing grants for regional water protection projects and creating a hands-on learning environment that prepares them for impactful careers in environmental science. And I am looking forward to this presentation. So, Rachel, you have the floor, and take it away.
All right. Well, good morning / afternoon, everyone. Thank you, Mark, for that introduction. I'm Dr. Rachel Rotz. I'm from the Department of Marine and Earth Sciences at Florida Gulf Coast University. I'm very excited to be presenting something I hope a little bit different than the norm today. So thank you so much for turning up and listening to this presentation. Today, I will be sharing some of the interdisciplinary approaches we're using to study water systems across a range of environments, from desert wetlands, yes, they do exist, to coastal ecosystems. And by understanding these different water systems, we can gain insights not only for environmental science and how that connects to water, but also for planetary studies. Okay, so the places you're going to go today, right? So this slide here kind of highlights the four unique locations that I'm going to focus on today that are pretty central to my work. We're going to be exploring desert and coastal wetlands across diverse environments, including Australia, Kuwait, Florida, and Hawaii. So each site offers a distinctive setting here where we can use an interdisciplinary approach combining geology, geomorphology, hydrology, even some chemistry, techniques like geophysical analysis, sediment sampling, groundwater modeling, and even remote sensing for us to gain insights into specific water system related topics for each location. So I'm an integrated techniques person, and I'm also an interdisciplinary scientist. And I just kind of feel that when we have a lot of tools in our toolkits, we can develop diverse and very creative methods to help us understand a more comprehensive and better understanding of water dynamics and how to bridge these environments together. So Arthur Clarke, which is one of my favorite authors, he has this famous quote, "This appropriate to call this planet Earth when clearly it should be called ocean." And I just feel like this quote is pretty special because it sort of reminds us of it's sort of a profound influence that water has on us, and that profound influence of water has on shaping planetary environments. So I've got Earth here, right? And alongside Earth, we have Mars and we have Titan, three very different planets with very different water histories. Titan actually has liquid methane, so a fluid history on the surface there. But, Earth is abundant in surface water. We know that. We have complex ecosystems, while Mars is an example where water once was there and disappeared, and it, may exist now in sort of trace amounts. And then Titan, as I mentioned, just has some really interesting geomorphological features that are kind of similar to Earth and similar to Mars, even though it has a different fluid kind of chemical makeup. There's some connections there as well. And so by studying Earth's water systems in diverse environments, such as deserts and coastal wetlands, we can gain insights not only about our own planet, but also helping us understand the potential for water and habitability on other planets as well. So these are kind of the things that I kind of hope that we can achieve in this talk. I hope that we can understand water systems in our desert and wetland environments a little bit better. We'll talk a little bit about nutrient cycles, sediment storage, and planetary analogs. So these are kind of like the 4 key points that I'm going to focus on with all the different parts of this talk. And I'm going to kind of give you sort of like a multifaceted like gallery display of a bunch of different projects that I've worked on from my PhD until current, to kind of show you how I'm sort of building off of all of that work and sort of bridging it together to kind of give us the sort of like very broad understanding of water systems and planetary analogs in coastal and desert environments. And so we'll start off with desert wetlands. And there I have the 2 locations that we're going to focus on the top. That's Australia on the left and Kuwait on the right for desert wetlands. And the 4 different integrated techniques that we use in these studies, like field techniques, laboratory analyses, remote sensing, and modeling. And so this slide here just shows you some examples of desert wetlands. A lot of people don't realize that desert wetlands even exist, but they do. The top 2 there are in the central part of Australia there. The one on the left is a flooded clay pan. That's just sort of a hard surface that forms in between dunes. And on the right there is an interdune lake. And so you can see that the areas they fill up. It's episodic, but they do fill up with water from time to time, enough so where there's some pretty unique ecosystems there that support some pretty amazing flora and fauna. And these are extreme environments where there's very little rainfall or very high temperatures. And so it's just really exciting to be able to work in an area where you don't expect to have water and there's plenty of it. And then on the bottom there, we have a depressional lagoon that's in Kuwait and a wadi channeled flood out. Again, Kuwait does get these episodic rainfall events and they do get flooding, and they have these low-lying areas that harbor lots of water and can harbor life. So I'll start off with Australia. So I did some work out in the Simpson Desert. This is in the center of the country here, continent. It's referred to as the dead heart because it's just so dry and so hot, and so many people have died trying to cross it, that it's just one of those very remote areas. It's absolutely stunningly beautiful. Like I said, it's in the center of the continent there, and it's in the Great Artesian Basin, one of the largest water storage systems on the planet. And the desert wetlands happen to be right in the northern part of the Great Artesian Basin there. You can see that it's highlighted in yellow within the continent map, and there's some arrows pointing there to kind of point you to the desert wetlands. I did a study in Lake Caroline, which is just north and east of the Plenty Lakes there. And these are 2 very prominent desert wetlands right in the middle of the dead heart. So just to give you some satellite images of what Lake Caroline looks like, over here on the left, we have a picture of Lake Caroline dry. It's an ephemeral playa, and on the bottom it's flooded. And so you can see that this playa actually does fill up with a decent amount of water from time to time. There is a linear dune field here that has transversed the area. But one of the things that drew me to the study was that Throughout the rest of the desert, you see these linear dunes pretty stabilized. Vegetation's growing on them. They are migrating some, but they're not degrading. But in these areas where we have this flooding occur, we see a full-on cannibalization occurring of these linear dunes, something that we don't expect to see in an arid environment during this part of this kind of climate regime. And so it was really interesting to find a spot where we were seeing linear dune erosion happening in real time. This is not something that you can pick up in the geologic record. And so we wanted to kind of get an understanding of what was happening with the lake here and its interaction with the dunes. And so we kind of went out to this area. It's pretty remote. Took us about a week in land cruisers to get out. We only had a sat phone to be able to communicate with the rest of the world, and we camped the whole time. And we did some, reconnaissance here, and we saw some of the typical signs of water. We saw channel incision through the Sill Creek mounds, desiccation. We even saw a dune collar. That thumbnail on the bottom right there, that's a ring around the dune, so to speak. We saw desert varnish, lots of signs that water was present, but this is so far remote that no one has any kind of flood record. Really, we have rainfall values from satellite images, but we really don't know how often this area actually floods and what kind of effect it's having on the degradation of the dunes and the sediment supply, what it's doing, adding to the sediment supply for the lake. And so we went ahead and augured 3 areas in the playa. That's me in there showing off my field skills, digging a hole. And we went ahead and did the 3 2-meter depth augured cores, so to speak. They were not intact, but we did sample the cores, and we did an XRD analysis with the cores. So we wanted to understand the composition of the dune material. And so we also grabbed samples of the linear dune that was sort of right there in the playa in that last figure, and we ran an XRD analysis, and we found that most of the material that's in the playa is very similar to the dune. It's quartz primarily with a little bit of feldspars. And as we dug down the playa at depth, we noticed secondary minerals forming like clays. We also saw salts precipitating out like halite and gypsum. And so we saw kind of this sort of very characteristic thing that we would expect to see in a playa that is filling up with water and drying out consistently throughout time. So we know it's getting wet. We know it's drying today. We can see that in the satellite data. We can see it physically flood. We look at the mineralogy here. We can see that it has minerals and composition indicative of flooding or wetting and drying. And then we can also look at the rainfall data that's available. Satellite images like NASA's GPM. And so I went through I'm sorry, was there a question? We good? Okay. I went through about 6,000 images, data sets over 20 years to try to figure out how many floods had occurred based on that satellite precipitation data. And so we kind of came up with a system to identify wet and dry days. And so what you're looking at here is a graph of rainfall, and those blue X's on the top are identified floods, so to speak. And then we went back through the satellite images and tried to actually get a visual eye on those flood events. And so we were able to observe 58 floods through 20 years using a whole suite of satellite images, Landsat, Sentinel, Rapid Eye, and we were able to identify 58 floods. So we know that that lake has filled up at least 58 times within the last 20 years, which is pretty exciting. Here is what one of those flood sequencing images look like. So you can see it was bone dry in January and February. Then in April, it fills up for a month. And then by May, it's bone dry again. So we're getting an idea of how much this lake is wetting and drying, and potentially sort of kind of starting to hone in on the effect that it could have with tearing down those dunes. The other thing that we did was we also sent the samples away for optically stimulated luminescence dating. This is when you take a quartz grain that's been buried and you sample it in the field without exposing it to any light, send it off to an OSL laboratory, which actually illuminates it within a very controlled setting and tracks how much energy comes off of the quartz grain to get an idea for how long that quartz grain was actually buried for. And so we did this, and we estimated that at the sediments at depths of 1.5, and 2 meters from the north center and the south parts of the playa, aged anywhere from about 16,000 to 58,000 years old. So we were able to actually even constrain a sediment rate here on the sediment that's in the playa at anywhere from 0.03 to 0.04 millimeters per year. So this kind of work here sort of gives us an idea of, you know, these desert wetlands that are kind of focused on these unique hydrological and geomorphological dynamics within an arid landscape. You know, we are looking at this sort of, you know, clay pan playa environment that experiences frequent but intense, you know, flooding events. We know it's playing a critical role in degrading the dunes. And we're using an interdisciplinary approach here, combining our geology, geomorph, hydro, and even some geochemistry to really analyze how these processes impact sediment storage and dune formation. We also use the OSL here, so we're able to look at the dates of burial for that. And so this is just a really good example to give us some insights about Australia's desert wetlands, how they can even planetary analogs for Mars. The way that the water alters the dune and redistributes sediments in Australia could mirror similar processes that might have occurred on Mars in its water past. And so I'm going to go ahead and pivot now to our work in Kuwait, where we focus on a different aspect of desert hydrology, which is groundwater storage. And so this slide here is basically highlighting our study that we did of freshwater lens formation in Kuwait's arid desert, okay, and its relevance here to wetland ecosystems. On the left, we see a map showing Kuwait's location within the Arabian Peninsula, and on the right, you see a detailed map of Kuwait, including elevation, that's white being the highest, kind of light green being the lowest, the major drainage pathways, and the locations of 2 known inland freshwater lenses marked by the red circle. So if you're hearing the term freshwater lens for the first time, they're isolated pockets of freshwater that sit above denser saltwater, serving as water resources in arid environments. We also have them over here in Florida, and we're going to talk about that in a minute too, as well as in Hawaii. They form when limited rainfall percolates into the ground, creating a layer of fresh water that floats on top of the salt water. And in desert regions where rainfall is sparse, these lenses are pretty special and essential to lots of flora and fauna in that area. Our research in Kuwait is focused on studying freshwater lenses to understand water storage and their sustainability. So this slide here kind of gives you a diagram of freshwater lenses, right, in coastal versus arid landscapes. So there's some different dynamics that govern the storage in each environment. On the left, we see a coastal freshwater lens. This is what we have kind of here in Florida. This is a very simple diagram, but what we have here in Florida, this is what you might see in Hawaii, which on the right is forming, this is a inland freshwater lens, which forms in arid regions. And this is what we're talking about here in Kuwait, and could potentially also have happened in Mars as well. Here, the freshwater lens lies above a saline groundwater in a depression or an isolated area that has recharge. And unlike coastal lenses, these inland lenses are especially vulnerable because they depend on minimal and frequent rainfall to sort of keep them sustained. And without recharge, they can quickly degrade or disappear. And so, you know, both of these kinds of lenses are pretty important for supporting ecosystems in their respective environments. For this study, we focused on the inland freshwater lens and trying to characterize that through physical and numerical modeling. And so I just want to give you an example of what a physical model could look like. If any of you guys are ever interested in building a physical model, it was a lot of fun. It's a lot of work to design it and then get the parts and pieces to put it all together. Supplies and the valves, but it's really rewarding when you can set the model up and you can run the model and you can actually simulate what you're doing. In this case here, you see a simulated freshwater lens and the yellow tracer dye there beneath our depression. And we went ahead and simulated several of these simulations, and we took measurements through time. This tank had a natural steady state flow, a transient state flow setup. So water was flowing out out. And so we were able to kind of measure the changes in the freshwater lens thickness and length through time. We videotaped the simulations. We were able to go back through the video footage and take our measurements and characterize how the freshwater lens changes through time, and how it can be sustained with different recharge rates. We also went ahead and designed a numerical model to be able to simulate this, and we wanted to simulate the exact conditions that we had created with the physical model. And oops, sorry, see if I can play this video. So this video here kind of shows you the simulation of the lens. I'm going to pause it right here because it actually goes really quick. But right here, you can see the freshwater lens. That's the blue material. And then you have the sort of color gradient here. And this color gradient represents the sort of interface here between the freshwater and the saltwater. And so we were able to simulate with the exact same dimensions with our physical model, the numerical model, applying our different recharge rates, simulating the freshwater lens, and then actually watching that freshwater lens degrade through time once it is no longer being recharged. And so you can see it there kind of migrating, sort of flowing right down gradient and eventually completely mixing with the rest of the saltwater system, the brackish water system that's beneath it until there's no remaining lens. So through those simulations, we did do some statistical analysis. And we looked at different lens thicknesses in the physical model versus the different lens thicknesses and lens lengths in the numerical model. We were able to get them to match within a reasonable amount of error. We also did look at the degradation of the lens. We wanted to understand how long it was going to take the lens to completely disappear with different recharge rates. We did create some models for that. And we came up with a calculation for a particular freshwater lens in Kuwait that we were looking at, and estimated somewhere between 20 to 200 years is sort of the lifespan of a lens once it no longer is being recharged, depending on different hydraulic conductivity values of the sand, because they can vary quite a bit. And so in Kuwait, I just want to kind of summarize that our research focuses on the formation and persistence of freshwater lenses, the isolated pockets. And in this case here, we have a pretty interdisciplinary approach involving geology, composition, stratigraphy, hydrology. This also includes our Australia work for desert wetlands. And it just gives us an idea here of the sustainability of water storage in the subsurface. And again, connecting this back to planetary analog insights is that our desert wetlands offer pretty valuable analogs for understanding similar landscapes on Mars, where isolated lenses could have supported past microbial life under certain conditions. All right, so I'm just pausing for a second because we are going to go ahead and now transfer over to coastal wetlands. So we kind of saw desert wetlands, and there's a couple of different examples of studies that can be done there, different disciplines and how those can be interrelated, and then integrated techniques on studying those areas. So as we move from exploration of our desert wetlands, where we kind of saw how arid landscapes adapt to minimal and episodic water availability, we can now look at coastlines and explore the interactions between freshwater and saltwater and coastal wetlands, starting with studies in Florida's barrier islands, and then moving on to estuarine inland wetlands in South Florida, and then lastly, Hawaii's lava tubes. And so this is work that I started with our students at Florida Gulf Coast University. And so one of the things that we did after COVID was venture out to the barrier islands there. I was kind of excited about this because I was sort of building on some of the work that I've done in the dunes and the swale structures and their depressional features that I worked on in Australia and in Kuwait. And so I was kind of excited to be in a coastal environment with some of those same features. And so it was a kind of a fascinating parallel, and kind of also very different. And so we went to Cayo Costa, and I kind of two kind of areas circled there in red. We looked at kind of a depressional wetland right there adjacent to that bay on the left. And then we also kind of looked at the groundwater situation and interdune swale there. And then on the right is Upper Captiva. This is a kind of a densely developed part of this barrier island relative to the rest of the barrier islands. It's a small sort of independent community that's sort of cut off. There's no roads or anything to get there. And they have a pretty interesting infrastructure established there. It's a pretty wealthy community. And so a lot of them have really nice homes, very well landscaped, with irrigation systems. And so we also wanted to take a look at what might possibly happening in the groundwater there beneath the developed area. So we have an undeveloped and a developed area that we looked at in these sort of depressional areas, the interdune areas of these barrier islands. I did want to showcase that these are student-run research projects here. So the work that I'm doing in South Florida that's focuses is on our coastal wetlands, is applying different techniques. So these students here were learning geophysical resistivity techniques. So on the left, you can see on the top left, there is an electrical resistivity meter. On the bottom is a ground penetrating radar. I have students on the top. That's student Haley Giroux. She used the electrical resistivity meter. And then DJ Heller on the bottom right there, he learned how to use the ground penetrating radar for us to be able to map the subsurface and take a look at the groundwater. Okay. And so, as I mentioned before, we have freshwater lenses in coastal environments. Florida is no stranger to that. And so when we did map the subsurface with these geophysical techniques, Haley's work, which is what you're seeing here, she presented this at AGU 22. She used her electrical resistivity meter here to look at the differences in the location of the freshwater to the saltwater from the dry season to the wet season in an undeveloped area. So what you're looking at on the top here is the geophysical data. The saltwater is that really dark blue region under the black dashed line there. And then the brackish to freshwater there is towards the top. And so this is what the sort of variable density groundwater environment looks like in the dry season. And then down there in the wet season, and this happened to be right, I think, after Ian, when she went out and pulled this data, you can see a very chaotic system with a much thicker brackish layer, and so salt water is being pushed down. So it was really interesting. We just, what we found was you can see a pretty significant increase in the lens thickness between the fresh season, the dry season and the wet season. And, this was an opportunity to sort of map that sort of inner dune groundwater system. So with the Kuwait work, we were kind of modeling it because we didn't have the geophysical data here in Cayo Costa. We were able to get sort of in a depressional environment where we know water accumulates and sort of recharges, percolates down and recharges the groundwater system and map that in the subsurface. DJ's work here, he used the ground penetrating radar to kind of take a look at the groundwater there in the freshwater lens. And he went ahead and used a technique where we looked at the radar reflection data to be able to sort of course out which points were reflecting off of unsaturated materials and which points were reflecting off of saturated. And this allowed DJ to kind of map the subsurface at that freshwater saltwater interface. And so these figures here on the right, where you see this like blue kind of line, that's where the freshwater saltwater interface is. He mapped that interface in the undeveloped part of Upper Captiva, and then he mapped the interface in the developed part. And, we have a pretty tight cross section there where we felt like we were trying to, constrain the comparison as best as possible. We did see a thicker freshwater wedge in the undeveloped area, which I think is something that is expected, considering that in the developed area, we do have several homes that have irrigation setups. And so one of the things that we could investigate moving forward is, could these be irrigation effects of why we're seeing, a much thinner or more sort of inconsistent interface in that sort of location that's beneath that developed area on the barrier islands. And so, yeah, so this slide just kind of wrapping up the barrier island part. And, as I mentioned, these are student-driven, projects here where they got to take a look at the subsurface, map those, maybe understand a little bit of effect on tidal, I think maybe Haley was kind of seeing storm surge effect there a little bit on that. And then, you know, potentially even looking at the anthropogenic effects of actually affecting that freshwater lens there in the developed area. I think that this is work that has merit, that's worth expanding. It was a wonderful opportunity for all of us to learn some new techniques and to be in a pretty amazing environment that is pretty unique, and look at these, you know, the relationship there between the surface water and the groundwater. So this is, again, as I mentioned, a multifaceted gallery of the different things that we've worked on. So these were the barrier island wetland areas. And now I'm going to shift our focus once again to move from barrier islands to the inland and estuarine wetlands within Florida. And so here we have the 3 locations inland. These are probably the locations I don't have to travel very far to do work. These are inland and estuarine wetlands right by FGCU. So we have the FGCU campus with half of it being conservation wetland area. So we get to do our living laboratory work out there. Bonita Bay, which is a engineered community that have these natural wetland systems sort of into the community, which is not too far down the road from FGCU. It's high density residential with golf courses and highly manicured landscapes. And then also the Naples Botanical Gardens Park, which is kind of more of our control environment, our more kind of relatively like pure environment, so to speak. And so students have done work out here too. We've had a couple, they've got to do lots of different things. They learned how to install their own shallow wells. So that's Laura Montalvo up there on the ladder. She's about 4'8", I think. And she's learning how to install her first shallow groundwater well. We have students in the center there sampling groundwater out of wells that have already been, it looks like that might even be purging and sampling. And then over there on the right, Jasmine Morjohn there, she's actually doing some water table monitoring. She's measuring the water table on FGCU campus and from one of the wells over there. So again, students getting to learn these different integrated techniques. Here's just some of the data from some of their work. This is on FGCU campus here. This is some orthophosphate work that was done. Again, looking at comparisons between the wet and the dry seasons. The first 2 maps that you see on the left are groundwater. So we see that we a higher concentration of phosphate, orthophosphate up there in the top part, kind of coming off of the dorms area. And then we see, you know, it kind of more flushed through the system in the wet season, and then more concentrated in the dry season. On the right there, we can see surface water, and we can see orthophosphate concentrations in surface water. And one of the things at this data, as well as the Bonita Bay data, which are both kind of mixed use, higher density used areas, is that groundwater had much higher nutrients in general than surface water did in these areas. Nitrate, nitrite, orthophosphate, phosphate, ammonia. Groundwater, you know, typically kind of beat out surface water in almost all these categories, which we found was really interesting. And we also saw this in Bonita Bay. And so this graph here that you're looking at, this is, you know, this is the Bonita Bay data. And you can see groundwater time and time again, for the most part, exceeds concentrations in nutrients over the surface ponds and the bordering streams. Here, the red lines, Imperial River and Spring Creek. And so that was really interesting. And this is work that's sort of like cumulative. It's work that students can go out to do to collect data. They can have different capstone projects. These are undergraduate students primarily, kind of sort of contribute and add to sort of like our growing kind of data to kind of really kind of, for me to kind of get an understanding of sort of what's really going on with groundwater versus surface water. There's future work that I have planned that gets into more of the modeling side, where we're working with a grant from NOAA, where we're really trying to understand the groundwater contribution to surface water, physically speaking, so we can understand chemically how much nutrients is really being contributed. I just want to show this last slide here. This is just a simpler graph of the park wetland that we looked at. And you can see here the nutrient concentrations for total nitrogen and orthophosphate were much higher in the surface ponds than groundwater in the park on the botanical gardens. And so, you know, I think this slide here, we're just kind of wrapping up the study, looking at the estuarine and inland wetlands in Florida, right? But we're seeing that the groundwater nutrient levels tend to be lower in the park wetlands. And, you know, we're kind of thinking at this point that the difference is likely due to maybe some of the natural filtration, more of it occurring in the park wetland. The botanical gardens does receive runoff from Naples, which is a pretty high density area around there. So we're thinking that maybe because the park itself has limited fertilization and has, you know, more purification or filtration capacity, that maybe the reason why we're seeing higher rates in the surface water is coming from that Naples side. I mean, in general, the rates were pretty low, you know, and they really didn't exceed any kind of thresholds that FDEP or the EPA had that kind of raised any eyebrows. But, you know, we are seeing just at the FGCU campus in Bonita Bay, higher concentrations in groundwater, which is kind of an interesting line of evidence to kind of pursue, to really kind of course out groundwater's role in nutrient contribution to wetland environments. All right, so I'm kind of skirt on through over to Hawaii now. And so I know it's kind of like a kind of a big break to go from Florida to Hawaii, but I think that the freshwater lens aspect and the coastal wetland aspect kind of does connect here. And so one of the things that I've kind of gotten myself into out in Hawaii a bit is looking at these sort of onchioline systems. And for those of you that have never heard the term onchioline before, they're typically found along coastal peripheries. We might have them here in Florida. I don't know of any. I know there's some down Bahamas and the Caribbean, and there are some in other limestone environments. In Hawaii here, we're in a basaltic environment, volcanic environment. But they're really like fascinating, sort of like extreme environments where like some really interesting critters live, a lot of nocturnal species, a lot of shrimps and different things. And so they're just they're neat systems where there's some macropore connectivity where the ocean and the groundwater system and the surface water, if it kind of makes it to the surface, are connected. And so what I kind of had gotten involved with in the last couple of years is actually investigating an onchioline pool inside a lava tube cave where there's a pretty big lake underground. And so I've got a white star here on the Hawaii map there on the bottom, and that white star is about where the lava tube cave is. And then I've got a black arrow on this freshwater lens diagram that I provided you of Hawaii here, and this is kind of what a typical oceanic island looks like, with the exception of some of those volcanic dikes to the left. We've got our freshwater, our saltwater, and our transition zone, and the black arrow is pointing to roughly where like an onchioline like system would form. So I'm just kind of giving you an idea for context. Now, I'm about to show you kind of where we went down into the cave. So I just wanted to kind of give you like a heads up that that's coming. So this is sort of what it looks like to climb down into a lava tube and approach an onchioline pool that's inside a cave. This is a pretty unique environment. I would say there's only a handful of these that exist on our planet. They make excellent planetary analogs for Mars research, given that Mars has very similar geology to Hawaii. That's us in the top left climbing down. It doesn't look as steep in the image, but it's a pretty kind of, treacherous way down. It's dark. We have some pretty high powered lights that we bring down there with us, but you're really climbing into like sharp rock that you can't see. And we don't really worry about snakes because there aren't any snakes in Hawaii, which is pretty cool. But I'm sure there's lots of interesting spiders and bugs, and I just try not to think about it. That's me getting into a floatable kayak on the top right there. I installed some sensors in these caves, and I wanted to measure the changes of the depth of the lake and its connection to the tides. And so you can see me on that bottom image, just kind of floating on in there. And so I'm trying to install my sensors. I've been working on doing sort of a framework of different kinds of Hawaiian basaltic, a geochemical framework of different kinds of Hawaiian basaltic aquifers, and sort of like proposing this as a potential hydrogeological or hydrogeochemical framework of groundwater that could potentially have been on Mars or maybe have remnants of it. And so this is a Piper diagram here of like the different kinds of geochemistries that we've put together. I put this together with a student from FGCU who graduated, Justin Wilder, a while back. And the red triangles up here, this is the geochemistry of tubes. So really high chloride concentrations, low to moderate calcium, low to moderate magnesium. So very much like an ocean signal, but not 100% ocean signal. My sensor data kind of shows depth versus tide. So we have, somewhat of a relationship there. And then we have salinity versus tide. Pretty noisy on this part. And part of that is because we do have groundwater that is also feeding the lava tube, and that is happening at different rates depending on the state of the tide. And so this is kind of one of the things that we figured out with the sensor data, was that when we get sort of in these first quarter and last quarter moons, there's sort of a synchronicity that changes between the relationship between the depth and the salinity with the tide, where that when the tide goes out really, really far, it gives an opportunity for the groundwater to sort of pool in. And so what I'm showing you here in this slide is a couple of circles surrounding those areas here where we actually see this sort of groundwater effect on the salinity, and we saw it with the depth slide as well, where we can see the groundwater effect in the tube as the tide is moving out. So very preliminary work, pretty unique. It hasn't been done. I'm kind of trying to build on it a little bit, hopefully try to publish it within the next year or two, but a fascinating way to kind of tie these variable density groundwater environments to some pretty unique wetland situations as well as planetary analogs. And so I just want to kind of try to synthesize this and sort of recap here through interdisciplinary techniques in geology, hydrology, and modeling. We're looking at ephemeral flooding, sediment storage, freshwater lens formation in desert wetlands, looking at in places like in Australia and Kuwait, getting insights into water dynamics in extreme environments, looking at planetary analogs for Mars. We're also working in coastal wetlands, right? Nutrient cycling, freshwater, saltwater interactions, potentially even tidal dynamics on things. I think the work in Florida and Hawaii kind of is interesting. It has more of a geochemical approach, but maybe offering some interesting environmental management, but also planetary science insights. Just again, getting a broader understanding on coastal wetlands and desert wetlands, and how we can use these areas as potential analogs on other planets, but what they can also teach us about wetlands in general. Future studies, I'm going to expand on my desert work. I'm going back to Australia this summer to continue to look at groundwater systems in some different locations, and also work more on the planetary aspect of that analog. I'll be working more. We're working in Florida now. We're doing some more work out on the Peace River Basin, understanding some dynamics with the Peace River and nutrient transport. So continuing to work in South Florida as well, probably go back out to Hawaii and get down in that dirty cave and pull some more data, because I'd like to take a look at some of the geochemistry of the rock there and understand the relationship between the lava tube. But, I hope that wasn't too dense and too all over the place for you guys. I just like to get involved in all kinds of interesting things and be creative. And I really appreciate you taking the time to listening to this presentation and staying tuned in. Also, I'd really just want to let you guys know how much I appreciate my students and my mentors, being able to teach and learn each other so much. It's pretty awesome. And we've had plenty of sponsors along the way. I work with Smithsonian Institution. I work with Society of Exploration Geophysics, water school has been tremendously supportive also of my work, getting started as an assistant professor. And so it's just been very generous and exciting to be creative and to sort of chase all of these really interesting things to kind of get a really broad understanding of these different water systems. So thank you.
All right, thank you very much, Dr. Rhodes. A round of applause for starters. A virtual one, you can't hear the crowd that's actually. All right, so we'll open up to questions. It's fascinating, though, the diversity you've got going. It's just amazing, literally, spatially, vertically, caves and surface and whatnot. So questions, let's go inside the room for starters. So Megan, if you see any hands or anybody just want to speak up, but if you can open up the mic inside the room, any questions, curiosities?
I guess I'll ask a question, especially about the cave research, just because when we're talking about like using it as an analog for Mars, like, I guess like thinking in future terms, like how you would apply that. You didn't like go super in depth, like I would be interested in like knowing a little bit more about that.
All right,
Can you hear me?
I can hear you. Were you talking about the Australian work? Is that what you said?
Yes.
Okay. Yeah. So, the linear dunes on Australia are kind of been this big draw for some of the research people that I've been working with, because linear dunes are one of the few really large sediment supply features that exist on other planets. We see linear dunes on Venus, we see linear dunes on Mars, and now we're seeing methane ice linear dunes on Titan. And so these really huge dunes store a ton of sediment, and they're really fascinating. And we really don't even understand on Earth, like, where all of the sediment came from. And we just realize that the Simpson Desert and these really huge ergs that we see out here are major sediment storage systems. And so one of the things I'm a water person. And so when I got dragged into this dune business, one of the first things that I was thinking about, well, how is the water affecting the dunes, right? And so I think that understanding the relationship between the water, and when I say the water, I mean the fluctuation of groundwater and the relationship between the surface water and the groundwater and how that affects dune stability, could help us understand how an environment on Mars may have functioned at some point in the past when there was liquid water on its surface, right? And so as we're learning more about what's happening on Earth, and we're understanding how these dunes evolve through time, how they formed, it'll help, and that relationship with water, it'll help us maybe gain some understanding on how that might have happened on those planets that have.
Question from Kathy Ewell on YouTube. Do you expect to find trapped lenses of groundwater in Mars?
I hope so. So, I mean, we literally have barely even scratched the surface of Mars. Like, we can't even dig more than 14 centimeters with our robots. So it's going to be a long ways away, I think, before we're going to really have a hard sample of water. There are geophysical missions on Mars that have looked at some different densities on the subsurface. There are papers out that claim that there's a lake underground. We definitely see layers of frozen ice. Mars has the largest shield volcano in the solar system, Olympus Mons. It's very similar to the shield volcanoes of the Hawaiian Islands. My thought is that if we have these really big basal freshwater lenses under our volcanoes here on Earth, if Mars did have a hydrological system and it had a Martian ocean, which some people think it did, why would it not had a huge freshwater lens beneath the volcano? And so, we may not find a live lens now, but we may find frozen water that had been somehow fresh because of a variable density situation on Mars. Great question. Thank you.
One more question from Matt Cohen on YouTube. Great talk. Thank you. Do you think there is a viable analog to Ankaline caves with coastal karst springs, especially ones that discharge offshore and tidal, e.g. Springs Creek near Tallahassee?
I think if you know of a spot, let's talk. Because, I mean, really all you're looking at is this sort of connectivity, this macro pore connectivity between the marine environment and the inland terrestrial environment. Of course, we have these cave systems up there. And so I'm sure we've got them that are, you know, maybe they're not a huge pore connected all the way out to the ocean. I know we have some blue hole situations right further out, but I'm sure we've got some conduits under Florida that are, you know, moving a bit of water back and forth through. So if you find a spot, Matt, you let me know. We'll go out there.
Anything else, Megan, on the live stream or in the classroom?
No, I think those are all the questions that we have.
Okay, I have one question, and it relates to that I love how you've integrated your students in your investigations and, you know, getting them up to speed on all the hydrologic techniques. And I had a question about the one student that had assessed that freshwater lens after Ian, and I'm curious, have they revisited that? And my curiosity is about how long does it, or is there any estimates of how long it might take to recover those lenses? I mean, we've had multiple events now, coastal flooding, and so you obviously disrupt it, but you know, the additional question is, and I guess it's dependent on rainfall, but any follow-ups for the particular assessment?
Yeah, we haven't been out. You know, Cayo Costa got completely destroyed, and the all of the bridge and the deck and everything got pulled off. So that data point that Haley got when she went out there, we kind of rogue took the boat out there and like kind of tied up to like a pole that was like, you know, tilted, and we went out there and got that data, but we haven't been back out since then. And, you know, I think, you know, one of the things I really want to do, Mark, is I would like to just install a well field out there, a shallow well field, and throw some sensors in there and collect data for a year or two. And we can go out and do the geophysics like 2 or 3 times a year, right? And kind of get like a baseline and match it up with the well data. But that's a project I really want to do. It's one of those like goals, career goals, I think could be really good for Barrier Island groundwater studies and looking at what's really happening in terms of the, you know, groundwater and the just sort of the saltwater intrusion. I saw a paper come out recently. I can't remember who wrote it, but they look at these like events, like these big events that sort of trigger the big changes and stuff. And I can't imagine with Helene and Milton and all of the water we've gotten, like even with Debbie, you know, we've got definitely probably some big changes out there since the last time we were out there.
Yeah, no, I would think so. And you've got the incremental, you know, increase of sea level rise. And then you like say these events. And fortunately, I would say if you instrument it, I guarantee we won't have some events for a while, but that would be a good thing. Maybe that's the trick.
Yeah.
All right. If there's no other questions, thank you very much again. That was really fascinating. I appreciate the presentation and your time. One more round of applause, please. All right. Thank you, Dr. Rhodes.
Thanks, everybody. Thanks, Megan, for setting this up. You guys have a great day.
Yeah.
Bye.